Hello everybody, my name is Matthew Johnson. Today we're talking about throughput optimization of proton therapy treatment centers. The article I reviewed is got a similar title, Optimizing Throughput of a Multi-Room Proton Therapy Treatment Center via Simulation. And this is by Stuart Price, Bruce Golden, and Edward Vaso. What you see there on the right is a gantry room, and that is where the proton beam from a cyclotron is administered to a patient. This proton beam is for the treatment of cancer, and it's less harmful and more effective than conventional radiation treatment due to the fact that it condenses, it makes a smaller, more precise area, and it doesn't give the body as much harmful radiation that kills good cells. This technology is very expensive, and it is on the cutting edge, is on the forefront. There are only, I think, 10 of these facilities in the United States. Because of how expensive this treatment is and how expensive the treatment facilities are to build, it's important to optimize the throughput, the amount of people per day that can be seen at one of these facilities. The article I read had optimization in 3 parts. One was the number and ratio of imaging and gantry rooms, imaging rooms connected to gantry rooms versus dedicated imaging rooms, and I'll explain what that is in the next slide, and determining the appropriate arrival schedule for patients in order to see the most patients in a day. So when a patient arrives at a treatment center, first they go into an imaging room, and that's where a doctor will line up and take measurements and image the cancer and figure out exactly where they're going to be administering the treatment to. This happens in the imaging room before the patient is then inoculated, strapped down to a certain chair, and then brought to a gantry room where the laser or the actual cyclotron will then be beaming in protons. There are 2 trains of thoughts on whether to have imaging rooms that are connected to gantry rooms, and therefore there's no wait time between the imaging room and the gantry room, or having imaging rooms that can service any one of the gantry rooms. And this is part of the model that I will be showing as to which one is best. Now, it's important to note here that even though the process goes from imaging room to gantry room, the cyclotron can only be used in one of the gantry rooms at a time. So that's another part of our modeling process, is the cyclotron actually having time allocations for each one of those rooms. So that's one of our bottlenecks. The research done for the article that I'm simulating gives mean times and ranges of mins and maxes, which I have represented for each part of the model that I'm about to show. It's important to note that 4 through 10 on here are all done in the gantry room. So I've actually got several servers in one specific room based on how many beam angles are going to be given. There's either 1, 2, or 3, and those will be different times for both the gantry room and for the cyclotron itself. In the simulation, you'll see patients moving from the imaging rooms to the gantry room. Imaging rooms are in blue and the gantry rooms are in red, and the cyclotron is that big microwave looking thing in the purple room. Now I fast forward into the model because it actually takes quite a long time to run. The cyclotron runs for 20 hours a day, and as you can see, this is actually the optimized result of all of my simulations, is that we require 5 of the imaging rooms and only 3 of the gantry rooms for a 99.8% use of the cyclotron. I used connectors instead of paths, which does not show the people walking because there was no distances were not part of my calculations for this. The actual floor plan and layout here's a summation of two parts of the optimization simulations that I ran. On the top here we have the connected variety, where we have the same amount of imaging rooms and gantry rooms because they are in fact connected, and only one of those reached a very maximal utilization of the cyclotron, whereas down here we have dedicated imaging rooms and gantry rooms separate, and two of these reached a very optimal level of scheduled utilization of the cyclotron. The best one that I was able to find was 5 imaging rooms and 3 gantry rooms, due to the cost effectiveness of having less gantry rooms, which are in themselves very expensive. One of the goals of the article was to reduce the wait time of each patient. They set a maximum of 10 minutes of wait time per patient. So using the ideal number of imaging and gantry rooms, I was able to come up with the optimal utilization of the cyclotron while keeping the average wait time under 10 minutes per patient. This turned out to be having a random exponential of every 6 minutes, and therefore patients should be scheduled to arrive at 6-minute intervals, and this accounts for tardiness and people that show up early as well. It turns out that my findings were quite a bit different than those of the people writing the paper. They had more gantry rooms and less imaging rooms, but by running the simulation, I believe I found better results with this configuration, and also they agreed with me that having dedicated gantry rooms is best, and I believe I was able to optimize further, having patients show up every 6 minutes instead of their prescribed 8 minutes. The lessons I learned are that it's best to map out a plan for a simulation of this magnitude, and definitely simulate before you animate, or you'll have to reanimate. And when the simulation results don't make logical sense, you've probably done something wrong. Anyway, thanks for listening. Have a great day.